on to the next one. Now again here we are going to use kinetic energy, and we are going to say the loss in kinetic energy is converted into the work done against friction. So it's the same case. You read exercise 5.3.
A police investigator measures street skid mark 27 long in an accident investigation. Assuming a friction force in car mass the same as in the previous problem, what was the minimum speed of the car when the brake locked?
Okay, so this is the same as the previous question. So can you take out your calculator and try this question? Okay, so we say that the loss in kinetic energy is the work done. So the police skid mark 27, assume the friction. So how much the frictional force is still the same, right? So the frictional force is, and the mass of the car is the same. So the frictional force, I think just now is 8,000, I think, 8,000 newtons. Let me use this type out. So over here, the frictional force is 8 Newton, 8,000 Newton. And the next one is the mass of the car. The M is 1,000 kilogram. 1,000 kilogram. So the distance traveled is 27, 27 meters. Okay, so can you calculate how much is the velocity? Let's say we refer to this one, right? We refer to this. Okay. Okay. So let me paste it over here, right? Paste it over here. Eh, okay, right. So I'm going to paste it over here. Okay. So now, can you use this relationship to calculate how much is the velocity, right? So the kinetic energy is the work done. M is 1,000. V, we don't know what is the velocity, right? This one is still zero. The force is 8,000, and the
Yep.
distance is 27. The distance here is 27. So can you calculate the V? Use this equation.
Okay.
You try.
So 1/2 times 1,000. We don't know V, so therefore it will be Z minus,
Zero. Because the final velocity is zero.
so it will be 500 V2 times 500
8,000
V2, 8,000 times
times 27.
27. Yes.
Yes.
So that will be 8,000, square root of 8,000 times 27 divided
Correct.
by 500, which will give me 20.8.
Correct. 20.8, right? Okay. So next we are going to look at this what they call the conservative force and non-conservative force. Okay, conservative force and non-conservative force. I delete off the previous one. Okay, okay. Right. So we're going to look at this conservative force and non-conservative force. Now, conservative force is, it doesn't involve the frictional force, right? Whatever energy that we have, we can still get back, right? Whereas in the non-conservative force, it involves the friction. So some of the energy is used up as friction. So in general, you just think that this conservative force, it doesn't involve friction. Non-conservative force involve the frictional force, right? So you read this conservative force. gravity is
Gravity
what?
is gravity is probably the best example of a conservation force. A diver has to work against gravity in making the climb. Once at the top, however, she can recover the work as kinetic energy by taking a dive. Her speed just before hitting the water will give her kinetic energy equal to the work she did against gravity in climbing to the top of the platform. A force is conservative if the work it does moving an object between 2 points is the same no matter what path is taken.
Okay.
Do I continue reading?
Yes, the second one, the
Uh,
non-conservative.
Non-conservative force is generally dissipative, which means that it tends to randomly disperse the energy of bodies on which it acts. The dispersal of energy often takes the form of heat or sound. Kinetic friction and air drag are good examples.
Okay, right. So conservative force, they say in this case is the gravitational force. Okay, now this gravitational force, you can actually get them back in the form of kinetic energy. See this? Where is it? Okay, okay. Okay, they say gravity is a conservative force because finally you will get the energy back in the form of kinetic energy. So in this case, the energy is conserved, right? Conserve here means we can get them back in the form of some useful form of energy. Let's say when you climb up the steps here, you are actually overcoming the gravitational force. But it is not all wasted because this force is actually conserved. When you jump down or actually you slide down, you will get back in the form of kinetic energy. But in the second case here, this one, non-conservative force. Now, we use a force to push the book along the surface of the table. This is also a force is used, but we cannot get them back because if you just push it around, right, the force is used to overcome the friction, so it is dissipated as heat and sound, so you cannot get them back like what we have in the first case, right? So this is used up, that you cannot get some useful form of energy, right? We cannot get the useful form of energy. Okay, so when they say the change in kinetic energy, delta ke means the change in kinetic energy is the sum of the work done against this conservative force and the work done by the non-conservative force. Okay, one more time. The change in kinetic energy, that means the kinetic energy used up. Why is it used up? It is used up to as a work done against the conservative force and also the work done against the non-conservative force. So it's used as both. Now, usually when you try to do some calculations, they will say, not this case, not the one that we have discussed so far, but the one that we have not discussed, they usually say that the work done against this non-conservative force is zero. That means they assume that there's no friction, no resistance. Okay, next one.